The concept of the light cone is a fundamental concept in physics, particularly in the field of relativity. It refers to the geometry of the spacetime interval between two events and provides a way to visualize the limits of causality in the universe. In this explanation, we will explore the concept of the light cone and its relevance to our understanding of the universe. Before we can dive into this, we need to understand a few concepts. The first is space-time. In relativity, space and time are not separate independent entities, but are instead intimately connected to form a four-dimensional space-time. This means that an event in space-time is defined by its location in both space and time. In other words, an event is not just a point in space or a moment in time, but is instead a four-dimensional coordinate t, x, y, z, where t represents the time dimension and x, y, z represents the three dimensions of space, and these two combined gives us a four-dimensional space-time. Secondly, we have the space-time interval. The space-time interval is a measure of the distance between two events in space-time. It is defined as follows, where ds is the space-time interval, c is the speed of light, dt is the time interval between the two events, and dx, dy, and dz are the spatial intervals between the two events. Note that the minus sign in front of the first term is important, as it indicates that time intervals have an opposite sign to spatial intervals in the space-time interval. The space-time interval is an invariant quantity, meaning that it is the same for all observers in any reference frame. This is a consequence of the fact that the speed of light is constant for all observers regardless of their relative motion. The space-time interval is therefore a fundamental quantity in relativity, and it has a key role to play in understanding the geometry of space-time. Now that we understand the space-time interval, we can move on to the concept of the light cone. The light cone is a way of visualizing the limits of causality in the universe. It is formed by tracing the path of light rays that emanate from a single event. The resulting shape is a cone with the event at the tip of the cone. To understand the shape of the light cone, we need to consider the space-time interval between the event at the tip of the cone and a nearby event. Let's consider two nearby events, call them A and B, and let's assume that A is the event at the tip of the light cone. We can calculate the space-time interval between A and B using the equation we stated above. If the space-time interval is negative, then event B is within the light cone. That is, it is the region of space-time that can be causally influenced by the event A. If the space-time interval, on the other side, is positive, then the event B is outside the light cone. In other words, it is in the region of space-time that cannot be influenced or that cannot be causally influenced by event A. We will give more details on this in a few moments. For now, the important point to note is that anything inside the light cone can potentially affect the event at the tip of the cone, while anything outside of the light cone is casually disconnected from the event at the tip of the cone. There are three types of space-time intervals that are particularly important for understanding the light cone: time-like, space-like, and light-like separation. A time-like separation is one in which the space-time interval is negative. That is, the two events are close enough in time and they could be causally connected. A space-like separation, on the other hand, is one in which the space-time interval is positive, which means that the two events are too far apart to be causally connected. Meanwhile, a light-like separation occurs when the space-time interval between the two events is zero. In this case, the two events are connected by a null geodesic, which is a path that a beam of light will follow in space-time. Events connected by a light separation are said to be on the boundary of the light cone. In Minkowski spacetime, which is basically a flat spacetime, the light cone is always a double cone that is symmetric around the events from which it originates. This means that the light cone does not have a convex or concave shape, but instead has a straight V shape. The portion of the double cone that extends in the future direction from the event is known as the future light cone. Meanwhile, the past light cone is the portion of the double cone that extends in the past direction. The boundary of the double cone is the set of events that are equidistant from the event in both the past and future directions. In a curved space-time, however, the shape of the light cone can vary from location to location and can be more complex than in a flat space-time. In some cases, the light cone can be distorted and can even have a convex or a concave shape, depending on the curvature of the space-time at that location. For example, in the vicinity of a massive object such as a black hole, the curvature of space-time is significant and can cause the light cone to be tilted or curved. In some cases, the light cone can be so severely curved that it becomes closed, which means that no light can escape from the region inside the light cone. This boundary of the closed light cone is known as the event horizon. In general, the shape of the light cone in a curved space-time is determined by the metric tensor that describes the curvature of space-time. The metric tensor determines the angles and distances between events in the space-time, and these factors determine the shape of the light cone. In summary, the light cone provides a way to visualize the limits of causality in the universe. The shape of the light cone is determined by the geometry of space-time and is dependent on the location and motion of the observer and the events being observed. By understanding the shape of the light cone associated with a particular event, we can gain insight into the possible causal relationships between different events in the universe. Thank you for watching, and I hope you find this useful. If so, mind dropping a like, subscribe, and I see you very soon to talk about another interesting topic.